Okay, everybody, let's make a start for this morning. Very good to see everybody here. Well done for finding it here somewhere a bit different today. So a bit of a change of scenery. So today, as I'm sure you guys can all read, the focus is we're going to be thinking about voltage. Now, who's done voltage before in some other courses? Okay. All right. Okay. Now, even if you haven't studied voltage before, I guess everybody has, we've heard of voltage before, right? Everybody's heard of voltage, comes out of the wall, you get 240 volts. We know that's a fair amount of voltage, or, sometimes you see things and it's high voltage, it's 100,000 volts, very dangerous, okay? So we've all kind of heard of voltage. If you studied voltage before, you kind of got some more insight on it. But if you're learning about voltage for the first time today, that's also absolutely fine. So today we're going to be finding out what voltage is, how it applies to circuits. But the thing I'd like to emphasize with this lecture, kind of the same as last time, is that we're really going to be focusing on the physics of voltage. So if you've done voltage before, maybe you've seen there's a few kind of nice little equations. It's quite easy to put some numbers in. You can calculate some stuff. But today we're really going to be thinking about where voltage comes from as a kind of physical sort of thing. That's going to be the focus. So we are going to get to those equations and try some examples, but we're really going to be thinking about how voltage comes about as something in physics and relating it to energy. So that's the plan for today. So I think let's start with a bit of a recap of some of the stuff from Monday when we were thinking about current and circuits and charge flowing in circuits. So where's the thing? Here we go. So this is a kind of pretty basic circuit diagram. Who's seen a circuit diagram before? Okay. So this is a pretty simple circuit, about as simple as we can get. So what's this part of the circuit doing for us? Any thoughts on this? Yeah, the back. Battery, yeah, very good. Here's a battery. So I guess it kind of doesn't look too much like battery. We've got the positive and then we got the negative here. Yeah. Right, okay. So strictly speaking, you might call this a power cell, and a battery is a combination of lots of power cells. So thank you for pointing that out there. But as far as I'm concerned, everybody calls these batteries. If you want to refer to it as a battery, I think that's just fine. But just remember, strictly speaking, if we only have one of them, it's a power cell, and a battery means we've got lots of them, okay? So thank you for pointing that out there. Now, what about this part of the circuit diagram? Can anybody recognize that? What's that part of the circuit doing for us? Yeah. Yeah, it's a light bulb. Very good. That's the circuit symbol for a light bulb. Now, you might see other symbols for light bulbs. Sometimes they kind of just draw in a little light bulb, make it look a bit more realistic, but that's quite a commonly used symbol for a light bulb. So if we think about this circuit going on here, this is a really pretty simple circuit. It's just basically a little battery and a light bulb. So I guess it's like maybe a torch or something like that. So I guess this is about as simple as a circuit can get. Now, if we've got a circuit, something that we're very often interested in is what's the current in the circuit? So we're going to have some current flowing through here. We want to know how much is flowing. So we'd want to use something like this. So this is actually a multimeter, but we can use this to measure the current with these probes here. Who's used one of these before? Quite a few people. Right. So this is actually a multimeter. It can measure the current and the voltage, depending on the setting. And then you just, you put the little contact somewhere in your circuit, and it tells you what the voltage is, or it tells you what the current is. So we're actually going to be using these multimeters in just a few weeks for our lab. So that's quite fun. You're going to get some experience with this. But suppose this is our circuit, and we said, okay, well, we want to know what the current is. So where should we connect an ammeter like this into our circuit so that we can measure the current? So I've got a few different options. So usually we just use the symbol A for an ammeter, but we've got options A, B, C, and D. So I'll get this question going, how to think about where in this circuit we would want to connect in an ammeter in order to measure the current. So just a hint with this one, remember that the current is the same in series. So think about where we'd want to place the ammeter so that we're going to get the same current that's flowing in the rest of the circuit. Okay, let's see what everybody thinks for this one. Where did we put the multimeter? Okay, so nobody's going for D. That's kind of not really doing much there. People are thinking maybe A, B, or C. Now, remember this idea that the current is always going to be the same whenever we're in series. So if we have something all in a line on our circuit, the current's always going to be the same there. So if we want to know what the current flowing through, the battery and the light bulb and the wires are, we're going to have to connect the multimeter in series here, like this one over here. So the correct answer is options. I guess you can't really see that. You can see it is the correct option. I promise that is the correct option there, option C. So very well done, everybody, with that question. Okay, that's the correct way to connect a multimeter if you want to measure the current. Okay, so when we get in the lab in a few weeks, if you want to be measuring the current in your circuits, make sure you're connecting it in series. Now we can start to think in a bit more detail about current flowing in circuits, and especially it's really interesting what happens at junctions like this. So we have places where the wires branching off going in different directions. And this business is actually described by what's called Kirchoff's circuit law. And this tells us what happens to current when we get to a junction. Now, as it's kind of drawn here, as it's written here, it might seem quite technical, quite particular to electronics, but it's actually a general statement about whenever we have current flowing. So in this situation, we're thinking about electrical current, but if you want to get a bit more intuition, is this really the same law as if it was, maybe current of water? So maybe we've got some water coming in here, and then it's going out in these two different pathways there. And what this law tells us is that the current is conserved at junctions. And you'll often hear physicists talking about conservation laws. We love that kind of stuff. And what we mean is that the current going in, same as the total current coming out. So based on that law, how can we describe this situation mathematically? Which of these mathematical relationships describes this conservation law mathematically? So let's see what everybody thinks for this one. Okay, let's take a look at this one. Let's see what everybody gets. All right, okay, fantastic. 100% for option A. So very well done, everyone, with that. Option A is the correct one. Okay, so that's the mathematical description of this. So even though it might sound a bit technical, current being conserved, it's really, as a mathematical statement, just stating that straightforward fact that the current in is equal to the current out. So that's what Kirchoff's current law tells us. Maybe let's try a kind of numerical example here. So now maybe we've jazzed up our circuit a bit. We've got two light bulbs going on here. And we want to think about what's the current going through both of our light bulbs here. So maybe we've wired in our first ammeter. That's telling us we're getting 3.2 amps. We're getting 5 amps from the total circuit. So let's see what we're going to get for the current going through the second light bulb there. So just remember with this one, current's conserved at junctions. So we can use that to figure out what the current going through the second light bulb has to be. All right, let's see what everybody thinks for this one. What's the current going through our second light bulb here? Okay, so looks like most people going for option B there. So I think you all got the right idea there. So we've got 5 amps going through the circuit in total. So if there's 3.2 amps going through this one, then we've got to have what's that? The 1.8 amps going through the other one. So correct answer is option B. So very well done if you gave that question a go. Okay. So I think that's all I'd like to say about, recapping current and circuits. So let's move on, start thinking a bit about voltage, so the main topic for today. Now, I'd like to approach voltage really as a physical concept. So not as a kind of one of these little circuit things and you get the equation, but I'd like to take it from a physics first point of view. And one of the things that physicists always like as a kind of classic physics example is actually roller coasters, okay? Now, you might say, well, how roller coasters, what's that got to do with, I thought we're learning about electronics this semester. What's that got to do with roller coasters? But what I'd like to do is start by thinking about roller coasters as a kind of example to think about for what's going on with energy, and then see how it applies to circuits. So maybe even if you have done some voltage before, this is going to be a slightly different take on it. So hopefully there's going to be something interesting for everybody, whether maybe you've done a bit of voltage before or if this is the first time you're thinking about voltage. So let's have a little think about this. And I'd like to start by thinking about the highest roller coaster in the world. Does anybody want to guess where the highest roller coaster in the world is? Any guesses? Any thoughts? Vegas. Who said Vegas? Oh, wow. Fantastic. 100%. Yeah, great. Do you know what it's called? Do you know what it's called? Oh, has he been on it? Did you like it? Oh, well, I mean, 100%. I mean, if I could give you bonus points, that is a great fact. So, yeah, sorry? Exactly. This is the trick. So the world's highest roller coaster, it's actually called the High Roller. And to give them credit for a very high roller coaster in Las Vegas, I think we have to give them credit. That is actually an excellent name for a very high roller coaster in Vegas, okay? And it's got a height proportionally of 277 meters, which sounds pretty high, okay? But as you said, okay, like most everything in Vegas, there's actually a bit of a scam to this, okay? So let's take a look at the world's highest roller coaster to see what's going on here, okay? So it's actually at the top of a building, okay? So technically it is 277 meters high, but only because they've gone and put the whole roller coaster on the top of a building, okay? So you only actually go, I don't know, what's that, maybe 10 meters, something like that, from top to the bottom of the actual roller coaster. I think it's since been dismantled, but this technically still holds the record for the highest roller coaster. So this isn't really the highest roller coaster in the world. Okay, let's take a look at what the actual highest roller coaster is in terms of, the height of the roller coaster. So it's this one over here. So King Dakar, 127 meters. Okay, so it just kind of goes along and then you just go straight up and come back down. It's quite similar to Stealth at Thorpe Park. Has anybody been on Stealth at Thorpe Park? Oh, okay, did you guys like it? No. Who likes it? It's good. It's good. Who didn't like it? Okay, see, I have been on it and I thought once was enough. I'm not going on it again. It's basically like this, but I mean, not quite as big. But this is the basic idea. You just go right up and you come right down. 127 meters, okay. Now, there is an important point to all of this, okay? And the point is that if you're thinking about a roller coaster, what's going to determine how exciting the roller coaster is and how fast you're going to go, it's not the absolute height of it, okay? So you can take a fairly kind of modest, fairly regular roller coaster, put it on the top of a building, put it on the top of a mountain, it's still going to behave in the same way, okay? What's going to determine how fast you go? It's the difference in heights, okay? And this is really the key to understanding energy and also to understanding voltage, okay? So this is the way I'd like to approach voltage today. It's really by thinking about the difference in energy and actually the difference in potential energy. So let's get a bit more technical, see what's going on here. So I've got a little graph here of energy versus position. Now, if that seems a bit kind of esoteric, we can actually think about this as, a roller coaster track. So maybe our roller coaster goes like this, goes down the hill, okay? You can imagine if you're sitting on a roller coaster, you roll down, you're going to pick up speed when you get here. And what matters, it doesn't matter how high or how low the whole business is, it matters what the difference in energy is between the top and the bottom of the roller coaster. That's going to determine how scary the roller coaster is to ride. Now, if we're thinking about this difference in energy for gravity, we've already seen what that energy difference is for gravity. Okay, so for thinking about gravity, that it's our change in energy, it's just that mgh. Okay, you guys remember that from last semester, right? Okay, so the mgh, so we know the mass, acceleration due to gravity, and the height. So if we were on Earth and someone tells you, okay, my roller coaster, it's, what was that, 170 meters high, then we can work out what the energy is. But let's generalize this a bit. Suppose we're not just sticking to Earth where that little g is going to be the same. Suppose maybe we're thinking we're on the moon or Mars, that little g isn't going to be the same. So then we'd need more height to get the same change in energy. So maybe what we could kind of think about is what I've kind of put in quotes here, a potential difference. So what I've done is if we just think about g and h, and that's going to equal to our change in energy divided by the mass. So for gravity, this is actually our change in energy per mass. And you might say, well, why is that a useful concept? And it would be a useful concept if we lived in places where this little g varied, okay? Because if this little g varied and we wanted to compare and contrast what our change in energy is, this quantity would allow us to do it. And it wouldn't depend on how much mass was sitting there, okay? So we can kind of think about that as a potential difference. Now, we don't usually bother with this quantity for gravity because we're almost always thinking about Earth and little g is the same, okay? So usually if we're thinking about gravity, we just say, okay, well, what's the height of my roller coaster? And then we're in business. We know how much energy we're going to have. So that's all well and good for gravity, but things get a bit more interesting when we're thinking about electronics, and the electrical force, okay? So for electricity, we can also define the change in energy, but instead of for a mass, for a charge. And we can describe what that change in energy is with the voltage here, that capital V. This is really where we get voltage from. So in this equation over here for electricity, this voltage, it's kind of doing the business, the same business as this G and the H are doing for us with gravity. So it's giving us some kind of measure for how much energy a charge is going to get, but without us having to say exactly what the charge is. So if we actually exactly wanted to know what our change in energy is, we'd need to know the charge. But if we just know the voltage, then we know how much our change in energy will be once we know the charge. So maybe it's going to be a coulomb or a million coulombs, then we'll know what the energy is. So same kind of idea for electricity. We can rearrange this equation a little bit and we get a potential difference, okay? So the voltage, it's the change in energy of a charge divided by what the charge is. So maybe we could think about an electron, that's a little something with a bit of charge, and it's moving in an electrical field. The change in energy is going to depend, well, the charge isn't going to change, it's going to depend on what the voltage is. Now, especially if you're seeing voltage for the first time, this might seem a bit kind of esoteric. Potentially, it might kind of make things a bit more confusing. But there's kind of one big take-home point that I'd like you guys to take away from this slide, okay? And what this is that when we're thinking about voltage, whether that's in circuits or just in general, we can kind of think about voltage as kind of roughly telling us as the same thing as height on Earth, okay? So if we're thinking, okay, what does 240 volts really represent? Or what does 100,000 volts really represent? You can kind of think about it as like the height, how much energy a charge is going to have once we know what the charge is. Now, hopefully that kind of gives us a bit of a picture of where the physics of this is coming from. But it might seem a bit confusing. So let's try a kind of numerical example where we put some numbers in. Hopefully that might kind of clear things up a bit. So suppose we're thinking about a defibrillator. Okay, so a defibrillator, you're going to come in maybe with 360 joules of energy, and there's going to be a potential difference of 200 volts between those two paddles, so when you're defibrillating someone. So based on this relationship between voltage and energy and charge, can we work out how much charge the defibrillator is going to shock the person with, okay, when we defibrillate them? So I'll get this question going. Let's see what everybody thinks for the amount of charge we're going to get. So remember, voltage, it's equal to energy per charge. And we have the energy and we have the voltage, so we just need to solve for what the charge is. Okay, let's see what everybody gets for this one here. Oh, okay, wow, 100% again. Fantastic. Okay, yeah, this is the correct answer. Okay, so very well done. It's the 1.8 coulombs. Okay, so very well done, everybody, with that. That's absolutely fantastic. Okay, so when you're defibrillating someone, 360 joules, you're giving them about 1.8 coulombs of charge there. So that's a kind of numerical example. There's another kind of really important thing that happens when we think about combining some of these quantities. So we've got the voltage over here, it's energy per charge, and we saw last time current, it's charge per time. So physicists always like thinking about what's going to happen when we combine these. So what are we going to get if we combine voltage with current? Which of these four options are we going to get? Okay, let's see which of these quantities are we going to get. Is this just too easy? Is this too easy for everybody? So, well, looks like everybody got that it's going to be power. Okay, so very well done with that. Okay, so let's try a quick numerical example of this. Okay, see how this works in practice. So maybe we've got a 12-volt battery, 30-watt light bulb. Let's see how much current we're going to get running through the light bulb. All right, so let's see what everybody thinks for this one. Okay, so some people going for A, some people going for B. So when we solve this equation, see what we get for the current, well, we get the 2.5 amps over there. Okay, so very well done, everybody, with that question. So we got our little circuit here, we got the battery, we got the light bulb, okay, and we're getting the 2.5 amps. Now, suppose we've got a circuit and we want to, bring in our multimeter and measure what the voltage is across a particular component. So let's bring back that circuit diagram here. So same circuit diagram as before that we saw for current. But what we're thinking about now is we want to measure the voltage in the lamp. Okay, so which of these places would we want to connect a voltmeter if we wanted to measure the voltage? Okay, so same diagram, but different question, okay? Let's see what everybody thinks for this one. All right, let's see what everybody thinks for this one. Where do we have to connect a voltmeter? Okay, so looks like some people thinking about A, some people thinking about option B there, okay? Now, very well done, everybody who gave this question a go. Now, I think the best place to connect your voltmeter, okay, if you are going to be looking at the voltage for this lamp in particular, it is going to be option B there, okay? So we're connecting it in parallel. We're looking at how the voltage drops as we go across the lamp. So I guess the best answer, it is option B, okay? But to give a bit of credit to the people who went for option A, for this circuit in particular, where we only have one lamp, we would hope that the voltage drop across the lamp is going to be the same as the voltage supplied by the battery. So if you did go for option A because of this particular arrangement of the circuit, I think you can kind of give yourself credit for that, okay? But what I would say is, in general, if we get to the lab, we want to be measuring the voltage across something, it's always best to go kind of direct to the source, okay? That's going to kind of minimize any uncertainty. But like I said, if you did go for A because of how this particular circuit's set up, then I think that's okay as well. So that's kind of pretty simple circuit. We just got one light bulb. What if we make things a bit more interesting? Now we've got two light bulbs here and we're measuring the voltage across both of them, okay? Now, the thing is, I think as everybody spotted, we have to measure the voltage in parallel, and that just means that's how we've got to connect our voltmeter, okay? So if we're measuring our voltage in parallel, okay, if we have components in series, okay, so just to clarify, we're measuring the voltage in parallel like this, but these two components are in series because they're all on the same line, okay? So if we're thinking about components in series, the total voltage drop across both of them, so the voltage between here and here, it's equal to this voltage plus this voltage, okay? So if we're thinking about voltage in series, this is the relationship for how to combine voltage. So the voltage drops as we go from one component in series to the other. So that's the basic setup for voltage in series. So I think last question for today, let's have a think about what the voltage is going to be if maybe, so we're using a 9-volt battery and we're running 2 lamps in series off our 9-volt battery, okay? And maybe we've only got 1 voltmeter, okay? And the first voltmeter, it's saying that the first lamp is getting 4.8 volts. Let's figure out what's going to be the voltage across the second lamp. Okay, so I'll get this question going. We'll see what everybody gets for this one. All right, so what's the voltage across our second lamp? Okay, it looks like people have got the hang of this. I think that's fair to say. It looks like, I think that's the most 100%. Okay, so look, guys, very well done with those questions. Okay, so I think that's a good place to wrap things up with voltage. Okay, so next week we're going to be thinking about some electrical components. We're going to be thinking about resistors. Can you guys see the tiny little resistor over there? And we're going to be thinking about capacitors, okay? So that's the plan for next week, okay? So excellent work with all these questions to everybody. Hope you guys have a great weekend, and I'll see you guys on Monday.